Yes, now we're looking at resultant and equilibrium forces. These two forces are forces that look alike that students confuse, but today we are going to clear them. Now, what do you mean when you say resultant force? If a body is this, let's say a car or an object that is meant to be moved, okay, and there is a force applied on this body, a single force. Let's say a force that is meant to move this body is F, and if that force is applied, this body will begin to move in this direction towards the right. Then if the same body is being moved with the same magnitude of force but with different forces, let's say one force here F1, one force here F2, maybe another one here F3, probably another one here F4, resultant force is that single force that is the same as putting these forces together. So I said if this is a vehicle and to take these four forces to move this vehicle to the right, and they do that, then if you remove these four forces and bring a single force that still does the same thing that these four forces did, it simply means that this single force F is the resultant of these four forces put together. So it therefore means that a resultant force is a single force that is equal in magnitude and direction to all the forces acting on a body. These are the forces acting on this body. The resultant of these forces acting on this body is this single force that has the same capacity of moving the body that these four forces were able to move and moving it in the same direction. So we define resultant force as a single force that is equal in both magnitude. Magnitude is like quantity of force, and in the same direction, equal in magnitude and direction to all the forces acting on a body. How do we now differentiate it from equilibrant force? What is an equilibrant force? Equilibrant force is still the same force as the four forces put together. The only difference is that it acts in opposite direction. Okay, if these four forces now are meant to pull this object to the right, F1, F2, F3, and the F4, if these four forces are meant to pull this object to the right, and then another force is applied to pull this object to the left, okay, that this force is preventing these four forces from pulling this object. So it means that as this force is applied to the left and these four forces are applied to the right, that this object will be at equilibrium and will not move. That means that this single force is an equilibrant force to these four forces put together. So an equilibrant force is a single force that is equal in magnitude, that is, it is equal in size, it's capable of opposing all these four forces, but in opposite direction to the effect of all the forces acting on a point. So you can see that this single force, unlike the resultant force, is in opposite direction to these four forces put together. So it means that equilibrant force is a single force that is equal in magnitude but opposite in direction to all the forces acting on a body at a point, or it is a single force that is equal in magnitude but opposite in direction to the resultant force. That is equilibrant force. So that is it. The resultant force acts in the same direction as all the forces put together and equal in magnitude, while the equilibrant force is opposite in direction. Okay, having known what resultant force and equilibrant forces are, we have to note that for a body to be in equilibrium, there are things we need to know. There are things that need to be taken into cognizance, one of which is moment. One of which is what we call moment. Moment of a force about a point is defined as the product of the force and the perpendicular distance of the force from the turning point to the line of action of the force. I repeat, moment of a force about a point is the product of the force and the perpendicular distance of the force from the turning point to the line of action of the force. Okay, if this is a pivot where an object, this is what you use to represent a moment of a force. So if you want to take a moment of a force from a point, this is the point where that is the turning point of the force, and then you apply a force that the moment of this force, if this is the distance of the line of action of the force from the turning point, say x, and this is the force, we say that the moment of a force about a point is about a point A. Let's use this point A. The moment of a force about the point A equals the product of the force and the perpendicular distance of the force from the line of action of the force to the turning point, or from the turning point to the line of action of the force. That is the product of the force and the perpendicular distance. Perpendicular because it's 90 degrees with the distance. Perpendicular distance from the line of action, from the turning point to the line of action of the force. This force times the perpendicular distance is what we call moment of a force about that turning point. Okay, where F is the force and X is the perpendicular distance. The unit of moment of a force is Newton meters, because the force is Newton and the distance is meters. So that is why it is so. Okay, we also look at moment of an inclined force. What if the force is not acting perpendicular to the distance? If, say, this is a pivot and a force is acting at an angle less than 90 degrees or greater than 90 degrees to the turning point, to the distance. If this is a force and this is a point A, this is point B, and this is the force F, okay, that the moment of a force about this point A, let's say the distance here is D, is the product of the force and the perpendicular distance. But this force, this angle is not perpendicular, so we have to resolve it to the perpendicular. Okay, we have to resolve it to the perpendicular. So if we are resolving it to the perpendicular, let's call the perpendicular resolution Fy. It means that the moment is equal to Fy times D, and you know Fy is not given, instead F is given, and the resolving a force away from an angle to the horizontal always tell us that resolving a force away from an angle, the simple thing we ought to do is to multiply the force with the sine of that angle. So Fy is F sine theta then times D. So the moment of a force of this force inclined at an angle less than 90 degrees is equal to Fd sine theta. So that is it. But if it is not inclined at an angle less than 90, if it is inclined at an angle 90 degrees or say perpendicular, then the moment of the force is just Fd. Then what if the body is inclined at an angle greater than 90 degrees, something like this? So if we have something like this, then we are going to be resolving it to the vertical like this, so that it will be perpendicular. So what we are going to do is that this is going to be Fy is going to be equals F sine 180 minus theta. If the angle is more than 90 degrees, it will be 180 minus theta. If the angle is less than 90 degrees, it will be theta. There is a mathematical proof of that, but that is not our concern now. So the moment about a point A will be equal to F sine 180 minus theta times the distance, and the distance, let's say the distance here is x, therefore it will be times x. So the moment will be equal to Fx sine 180 minus theta. So I said if it is angle greater than 90 degrees, you have 180 minus theta. If it is angle less than 90 degrees, you have just sine theta, sine that angle. But if the force is completely perpendicular to the distance from the turning point, then it is just force times distance. That is moment of a force about a point. Then we will look at equilibrium of parallel forces. Equilibrium of parallel forces. In equilibrium of parallel forces, there are two conditions for a body to be in equilibrium when it is acted upon by parallel forces. Okay, and the two conditions are force condition and moment condition. Okay, if what we are saying is that if I have a body that is acted upon by a force, maybe a downward force F1, maybe another downward force F2, maybe an upward force F3, maybe another upward force F4, let's say there is another downward force F5, okay, and then we have a distance. Let's say we want to take moment. When you are taking moment of a force, it must be about a point like we discussed. So if you are taking moment about this point F1, okay, let's say point of A, then the distance, if the distance of this is x1, let's say the distance from here to here is x2, let's say from here to here is y1, and let's say from here to here is y2. Okay, that is just, it's not convention, it's just what I chose to use. So if we are talking about the force, which is one of the conditions for this body to be in equilibrium, this body now, that's this plane to be in equilibrium, is a condition of force. And what it states is that the resultant of all the forces that acts on the body must be zero. That is, if we find the resultant of all these forces put together, that it should be equal to zero. And what is the resultant of the forces? The resultant of all these forces will be equal to, you either take these ones to be positive and these ones to be negative because they are acting in opposite direction. So we are going to have F1 plus F2 plus F5 plus F2 because they are parallel, then minus F3 minus F4. This is the resultant of these 5 forces, and it will give us 0. If it doesn't give us 0, this body is not in equilibrium. So for this body to be in equilibrium, these parallel forces acting on it, should the resultant of all the parallel forces acting on it should be equal to 0. Or in another way, we can say the sum of all the forces acting on that body in one direction must be equal to the sum of all the forces acting on it in opposite direction. That is another way to state it. So that's, in that case, we have that F1 plus F5 plus F3 is equal to, is plus F2, sorry, that is F1, F5, F2, these three are acting in one direction, is equal to F3 plus F4 acting in opposite direction. So it does not matter how many forces. So it means F1, F5 and F2 is equal to F3 and F4 because F1, F5 and F2 are acting in the same direction, while F3 and F4 are acting in opposite direction to them. So it does not matter how many forces are acting upwards and how many are acting downwards. But for this body to be in equilibrium, the sum of all the forces in one direction must be equal to the sum of all the forces in opposite direction, or the sum of all the forces acting upwards is equal to the sum of all the forces acting downwards. That is the first condition. Then when we look at the moment condition, the moment condition has to do with taking moment about a point. It says that the sum of the clockwise moment about a point is equal to the sum of the anti-clockwise moment about the same point. The sum of the clockwise moment about a point is equal to the sum of the anti-clockwise moment about the same point, and that is what we refer to as principle of moment. That's what we refer to as principle of moment. So if we look at this diagram, if we want to take a moment about point A, one thing is that if you are taking a moment about a point, then the force acting at that particular point is not taken into consideration, is ignored. So if you are taking a moment about point A, F1 is not considered because at this point now, that is where all the forces are resolving. So if we take the moment, like we say, is the product of the force and the perpendicular distance from the turning point to the line of action of that force. So if we want to take the clockwise moment, let's take all this force, that is these 4 other forces go to A. If this one goes to A, it is going in this order. This one goes to A, going in the same order. If this one F5 goes to A, going in this order, F2 goes to A, is going in this order. You see that these F5 and F2 are going in the direction of the clock, that is clockwise, while F2 and F4 are going in opposite direction of the clock, that is anti-clockwise. So if we want to represent that, we are going to take a moment now to see how that happens. So it means that the moment of F3, sorry, is the F3 times the distance of F3 to A, which is y1. So the moment of F3 is F3 times y1. Okay, going in anti-clockwise moment. So we are going to sum all the anti-clockwise moment and equate it to all the clockwise moment, because the moment principle of moment states that the sum of the clockwise moment must be equal to the sum of the anti-clockwise moment, just like the principle of force say that the sum of the upward forces must be equal to the sum of the downward forces. So this is the moment of F3. Another anti-clockwise force is F4. So we say plus F4 times y, is it y2? No, y2 is from here to here, not to the A. So we are going to take a moment of F4 to A. Remember, it is the same point. And the distance of F4 to A is going to be adding y1 and y2. So it is going to be F4 times y1 plus y2 Okay, so these are the two moments in anti-clockwise direction. We equate it to the moments in clockwise direction. So how do we do that? So if we take moments in clockwise direction, the first one is this f5. f5 to a is f5 times the distance x1. So it is going to be f5 times x1. Then plus the second one is f2 to a is going to be f2 times the distance. And if you look at the distance of f2 to a is x2 and x1. So it is going to be f2 times x1 plus x2, and that is what we have as the moment. This is the anti-clockwise moment, this is the clockwise moment. So this will make this body to be in equilibrium. That is the condition for moment, or the principle of moment. Okay, and sometimes if two forces are acting in opposite direction, we have what we call a couple. So what is a couple? A couple are two equal but opposite parallel forces not acting in a straight line, creating a turning effect on a body. Okay, if you have a body and a force is acting this way, another force is acting this way, you see that it will create, if this is the turning point, it will create a turning effect. This body will be rotating in this order. If this force is acting this way and this force is acting this way, this one is pulling it up, this one is pulling it down, it will be rotating in this order. And that is what we refer to as couple. The distance between the two forces, say, is d, and this force is f1, while this other force is f2. So the distance between them is d. So we say that a couple are two forces. This f1 and f2 are the couple. They are two equal but opposite parallel forces that is not acting in a straight line. Two equal but opposite parallel forces. They are not acting in a straight line because it creates a turning effect on the body. As this is going up and this is going down, then a turning effect will be created and this body will begin to turn in this order continuously. Example of a couple will have two fingers turning a tap and forces on two hands turning a steering. If a driver is using two hands to turn a steering, that is a couple. Just like we have moments of a force, we also have moments of a couple. We also have moments of a couple, and that is just like moments of a force is the product of the force and the perpendicular distance of the force from the turning point to the line of action of the force. The moment of a couple is the product of one of the forces and the perpendicular distance between the line of actions of the two forces. One of the moments of a couple is F1 times D, the one of the forces and the distance between the two forces, or F2 times D. That is what we call moment of a couple. A moment of a couple is known as a torque. Moment of a couple is known as, that's what we refer to as torque, the product of one of the forces and the perpendicular distance between the two forces. Okay, factors that determine the moment of a couple or torque are: number one, direction of the force. The direction of the force determines the moment. The magnitude of the force, that is the size of the force, what the value of the force also determines it, and the perpendicular distance of the force from the pivot. This distance also determines the moment of a force. The moment of a couple is determined by the distance, the magnitude of the force, and the direction. These are the three factors that determine the moment of a force, of a couple. We are going to take examples to see how questions under moments and equilibrium and resultant of forces are being handled.